Very good evening to you, student. Today I'm going to discuss with you the theorems on if f defined from I to R is strictly increasing on I, where I here is closed interval, then f inverse defined from fi to r, or g we can say defined from fi to r, where g here stands for f inverse is again strictly increasing and continuous on f of I. So what is the given condition is that f defined from I to R is strictly increasing and continuous. And continuous. Okay, f defined from I to R is strictly increasing and continuous on I. Then what we need to show that the inverse also is again strictly continuous and strictly increasing and again continuous on f of I. So here we consider f is strictly increasing. Now, what is another condition is that since f is continuous, it implies that f of I here is an interval. Because we have proved this theorem, if f is continuous, it implies that f is bounded on that closed interval, and moreover f attains its bound, that is supremum and infimum on that interval. So using that theorem, if f is continuous, then we have f of I is an interval. Now this follows here by preservation of interval theorem. Now f is since f is strictly increasing, okay, strictly increasing, then f is injective or 1 1. What does it mean? F here is strictly increasing, then f is 1 1. So if f is 1 1, we know that the inverse of a function exists if f is 1 1 and on 2. So here, since f here is 1 1, because f being a strictly increasing function, so there exists g defined from f of I to I, where g here is equal to f inverse. Okay, why this inverse exists? Not only 1 1, because it is also on 2, since the range of this function is defined on f of I. So clearly f here, f is 1 1 and on 2 on this interval fi. So therefore there exists an inverse, say g here, which is equal to f inverse. And what we need to show is that this g, we now show that g here, which is called f inverse, is again strictly increasing. And for that we take, let y1 y2 belong to f of I. So y1 y2 belong to f of I with y1 less than y2. So y1 y2 belong to f of I, so there exists x1 x2 belong to I such that f of x1 is equal to y1 and f of x2 is equal to y2. So what we have to do is that in order to show that this f inverse is strictly increasing, we have to show that x1 is also less than x2. So we must show that x1 is less than x2. Otherwise, if x1 is greater than or equal to x2, what we will get? It implies that f of x1 is greater than or equal to f of x2. Why? Because since f is strictly increasing, so by definition of strictly increasing, x1 greater than or equal to x2 implies that fx1 is greater than or equal to fx2, since f is strictly increasing. Now, so this implies, but what is f of x1? This implies that y1 here is greater than or equal to y2, which is not true, because here we have taken y1 y2 belong to f of I with y1 less than y2, and what we need to show is that x1 is less than x2 for any x1 x2 belong to I with f of x1 is equal to y1 and f of x2 is equal to y2. But what here we assume that we have to show that x1 is less than x2. Otherwise, if x1 is not less than x2, it means that x1 is greater than equal to x2. So from x1 greater than equal to x2, it implies that fx1 is greater than equal to fx2, since f is strictly increasing. And what is fx1? It is y1. So this, which is a contradiction. And why this contradiction arises? Because we have assumed here, since y1 is less than y2. So therefore, why this contradiction arrives? Because we have assumed here x1 is greater than equal to y2. So this implies that y1 here, this implies that y1, f of x1 must be less than x2. So x1 must be less than x2. And what is f x1? So you apply f of x1 is less than f of x2, which implies that f inverse, or we can say that g here, which is, that is, so y1 here is less than, which is a contradiction. So therefore, we have y1 here is less than y2, which implies that f inverse of y1 is less than f inverse of y2, which implies that x1 here is less than x. What is f inverse of y1? F inverse of y1, you apply f inverse on both sides. What we have is that f inverse composite f gives you identity function. Identity function I of x always gives you x. So we have x1 is less than x2, or we can stop here and leave it y1 less than y2. It implies that f inverse of y1 is less than f inverse of y2, implies that f inverse is strictly increasing. Next, it remains to show that f inverse is continuous on f of I. So let's C prime here. Let C prime be any point belong to arbitrary point on f of I. Now we shall show that G here, which is called to f inverse, is continuous at C prime. Now since C prime belong to f of I, so there exists C belong to I, such that f of C is equal to C prime. So that you apply now f inverse, which apply f inverse on both sides, because f inverse exists, f of C is equal to f of C prime. F inverse of f here, f of C is nothing but f inverse composite f inverse composite f of C is equal to f inverse of C prime, which implies that f inverse composite f gives you identity function on C gives you C is equal to f inverse of C prime. So let epsilon greater than 0 be given, then C minus epsilon is always less than C is less than C plus epsilon. So for any C belong to I, you take any epsilon greater than 0, then you subtract C minus epsilon is always less than C less than epsilon. And since f being strictly increasing, it implies that f of C minus epsilon will be less than f of C less than f of C plus epsilon. So let us take delta to be the minimum distance of this f of C minus epsilon, f of C minus this, or f of C plus epsilon minus f of C plus epsilon minus f of C. Then Clearly f of c, because we have here f of c minus epsilon is this, so clearly we have f of c minus epsilon will always less than or equal to f of c minus delta less than or equal less than f of c plus delta less than f of c plus delta, where delta is the minimum among this. So clearly f of c minus delta is greater than this, and it is less than f of c plus delta, but strictly less than f of c plus epsilon. So hence for all y satisfying this interval, f of c minus delta less than f of c minus delta less than y less than f of c plus delta, we have here f of c, because this y lies between this, for y lies between these two, it implies that f of c minus epsilon is less than y, because this is less than y, so obviously this also will be less than y, is less than f of c plus epsilon. Now since f inverse is strictly increasing, we have f inverse apply on this f of c minus epsilon is less than f inverse of y less than f inverse of f of c plus epsilon, and by taking the composite of this, what you have is c minus epsilon is less than f inverse of y is less than f inverse composite f gives you identity, so this is c plus epsilon. But what is f of c? F of c here, but c here is f inverse of c prime. So I'll replace this f inverse of c prime minus epsilon is less than f inverse of y is less than f inverse of c prime. Replace c by c prime. We have obtained here this one. Okay, this one, c is equal to f inverse of c prime less plus epsilon. So what we have here is this. From 2 and 4, from this relation, this, and the other one, that is f of c minus, from this and this relation, what we have is that mod f inverse of y minus f inverse of c prime is less than f inverse of y minus f inverse of c prime is less than epsilon when mod y, when here you can use this relation. Where is that relation? Okay, that equation 3. Okay, mod y minus c prime is less than epsilon. Okay, this one. So you replace this one, it implies from here c prime minus delta is less than y less than c prime plus delta, because f of c here is c prime. So using this and this relation, we have mod f of using this and this, we have whenever mod y minus c prime is c prime. Okay, when mod y minus c prime is less than delta. So thus we have shown here that for every y, for given epsilon greater than 0, there exists a positive number delta greater than 0, such that for all y belong to f of I satisfying c prime minus delta less than y less than c prime delta, we have mod of f inverse of y minus f inverse of y prime is less than epsilon. So this shows that f inverse is uniformly continuous, sorry, c prime here, f inverse is uniformly continuous at c prime, but c prime is an arbitrary point of f of I. So this shows that f inverse is continuous on f of I, which completes the proof.